Well, I mean, yeah, but that'd be unprofessional.
Off the record.
I mean, for something like this where I'm going to just be in between classes anyway, so I might as well answer questions. Yep. No. I mean, so I mean, the grades at the end are going to be scaled. And so, I usually, usually I don't do anything until the very end of the class. But for the electives, I usually like to have the class after the electives around around 80%. And so if the class average is below that, then I can add one bit. Yeah, I don't do that till the end, because typically for the midterm exams are going to be averages below 80%. That's just kind of how they estimate it. But usually with the homeworks, if you've been keeping up with that, and then with the final projects, usually the final project grades are higher than the midterm, then things usually average out. But yeah, yeah, I mean, usually for the electives, unless you haven't been doing anything, then usually you end up. That's not to mean you shouldn't study. You should still study. You should still do the final project, but I'm not trying to fail.
I don't remember, do you have any, grade switches? Anything where if you did better on the second one?
Yes.
Replaces the others?
Yeah. Yeah, if I have that I don't have that for finite elements, we don't have one exam.
Right.
But for optimization, whichever exam you do better in, I'm going to count that one for 50% more points.
Oh, great.
Yeah.
Oh,
So-
that's right, it's the distribution.
Yeah. So whichever exam you do better in, that's when you work 30% of your final grade. The one that you do worse in, that's when you work 20%.
You don't drop any homeworks though?
I do. I drop the lowest one.
You don't drop the lowest one?
The one that just passed my list. I don't understand trust. And I know you sent the result, I was like,
Yeah.
I can't just copy those. I don't understand it.
If you just copied it, you're going to be screwed on the exam. So you should definitely know how to do that.
I don't understand trust. Did you already do the review? I'm doing the review today.
We're not doing the review. Doing something else.
I'll be back.
We will not be back.
I will be studying. Trying to figure out how trust is work. The only ones that, because you'll see on the homework, I did the first trust problem, and then I was like, yeah, I got 3 hours, I can finish this homework. Did the trust problem, took me 1.5 hours, and I'm like,
Yeah.
I'm gonna do a moment. I'm gonna do the torture. Then I finished that one in 30 minutes, and I'm like, I got class at 9 a.m. I'm going to bed. Oh, I was gonna ask.
Yeah.
We have 2 graduate students I want to initiate.
Okay.
And then I recently found out I have to find out their bachelor's, their master's that they're pursuing when they finish, and they're pursuing a doctorate.
Okay.
I don't know how to do that. Oh, yeah.
Give me their names. I'll reach out.
Because from what headquarters told me, they're not supposed to fill it out. I was gonna ask them to. Because we also have to talk to their academic advisor, and they need a signature from their academic advisor. Your signature and my signature, the verified, if you can send it to everyone.
So their advisors, their graduate advisors on my own. But yeah, give me their names. Yeah, and give me the information and then I can reach out.
Okay, I can give you the names probably right now.
Okay. Yeah, just send me, and then you said their study plan before they came here at the previous institution.
It seems like it. I guess what I'm sort of wants to see basically if they rejected the offer initially.
Oh, so rejected when they were an undergrad. I see. Okay.
Because if it did, then they can't.
Oh, interesting.
I didn't know this.
Oh, I didn't know that either. I mean, it could be that they weren't eligible at that, or maybe they're under.
No, that's a whole different thing. Like if they're not eligible, that's one thing.
Yeah.
The other thing is if they just rejected the offer and why, like if they just didn't respond, or if they flat out were like, no.
Okay. Well, give me their names and then I'll reach out.
We'll do.
Yeah.
But besides that, we got approval for. Yeah, we got approval for Friday. Will you be participating in initiation this Friday?
This Friday? Yeah. Yeah, I'll be here. 7 p.m. this Friday. Okay. Yeah, I'll be there.
Okay, we have more people than we need.
Okay.
And I think I will go study these trusses.
Okay.
I don't get it.
You should definitely do that.
Like I saw it was 0.5. So I'm
Yeah.
like, okay, everything's 0.5.
Uh-huh.
Oh, okay, so these two blocks are negatives. Okay, this makes sense. And then
Uh-huh.
I go to the next problem and I'm like, wait, this isn't the same pattern. Wait. And then the springs, I'm like, oh, this connects to here, this connects to here. Oh my God, it's just, oh, this is so easy.
Yeah. The 2D trusses are hard. Yeah, make sure you go over the examples.
Well, just as a question, are we gonna be allowed to use MATLAB
No,
on the exam?
but you're also not gonna be solving anything.
You're just solving like the array.
Exactly. So I just want to see the matrix. So you set up the matrix, you apply the boundary conditions, and then that's.
And you expect us to write like the boxes, like the dotted boxes?
You don't have to, but it helps to make sure that they're in the right place.
You'll see my homework, I just wrote like plus, plus,
Uh-huh.
plus,
That's fine.
plus, instead of overlapping them, I'm just like.
Oh, yeah, that's fine.
Yeah, plus, 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 plus.
As long as I can follow it, and that's.
Okay, so you just want the elementary, the global, and then the boundary conditions.
Exactly,
applied, And then
exactly,
that's the last one you.
exactly. Yeah.
Okay,
No solving. That would take. It already takes a long time to write the matrices.
I'll be honest, by the time you give me the exam, I'm skipping the trust one and I'm doing the other. I'm doing the.
Well, there's only two problems. If there's three, we wait.
And if you just strings, you just put two.
There has to be a trust problem.
I know, I get it. It makes sense. Okay, I think I'm gonna go study then. just
Okay.
'cause We have the whole next, wait. Oh, wait, no, it's Tuesday, Thursday, we're fine. I was gonna ask if we're meeting up next week and because.
Oh, yeah,
We have
yeah.
the one Monday.
Yeah, we have the 1 month. Yeah, this semester is weird.
Next Monday is not.
Yeah, next Monday's not off. I'll be here.
Why do we not?
Thursday.
I mean, fall semester, we always have a lot of Mondays off. But I think because this fall semester, we started so late and we're going so late, so I think they have to add one extra day just to make it.
A lot of people.
I know.
But okay, I'll email you the name right now,
Okay,
so maybe we can get the names, if not, they're gonna be at Count Poly on December 6th.
okay. Question in the chat, can I explain again the concept importance of symmetry in FEA? Is it to reduce computation time and therefore cost? Yeah, that's the main thing. So if your model has any symmetry, and you can basically cut your domain in half, that's basically half the cost. And so for a lot of problems, half the cost is huge. So after we come back from Thanksgiving, we're going to be talking about, ways to kind of reduce cost in simulations. And so symmetry is the #1 way that you can reduce cost.
So, taking that, if I want to find what's happening there, it's this component using that angle, right? So it would be a little bit less.
Good.
Yeah, I just, I don't remember if I had anything.
Okay,
I'll send an email.
Then I do that same thing.
You can possibly help initiate.
To find
Okay.
the component.
yeah, just send me an email, remind me about initiation, and then I'll,
Email to everyone at
Force now.
there's like 9.
Figuring out how
Nice.
to do it this way.
Would you like to go to the old spaghetti factory after?
So,
I'll see. I'll think about it. Yeah. Oh, okay. Okay, sounds good.
so
You too.
then, averaging. Then using that. So that. And there. So it's slowly dropping and dropping. Which makes sense. Yes, this is what we were doing.
Oh, okay, it's 5:30. Okay, let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
capacity today.
Good to hear.
So
So excited to take exams. I'm excited for them to be done too. So it's a lot of grading for me, but, okay. So today, we're doing something new. So, we're basically done with all the content that we need for the exam. So, from here on out, we're moving into the final stages of the semester. So, we've already talked about the final project. So you guys kind of know what that's all about. So everything that we do from here on out is kind of in support of your final project. So today we're going to be going over validation and verification, or V&V. If you remember when we talked about the final project, I think it was last week, that was kind of an important part. And so we'll go over that, what that means, and what you have to do for the final project for that. And then when we come back from Thanksgiving, I have a few lectures. At that point, it's really going to be up to you. So, I have a lot that I can talk about for finite elements. I have one more activity that we can do. But it's kind of whatever you guys want to hear about finite elements and whatever is going to be helpful for you guys on the final project. So, we'll talk more about it after we come back from Thanksgiving, but just know that, it's all just kind of cleaning up kind of loose ends at this point. Okay. Okay. But I'm sure that the big thing on people's mind right now is our midterm exam on Thursday. So that's going to be here in class. I think that'll be the first and only day that I see everyone here in the class at the same time. So that'll be nice for that, but the exam itself will be stressful. So I'm working on the exam, so I'm pretty much done with it. So I can tell you right now that there'll be 4 conceptual short answer questions. There'll be 2 finite element problems. One of those is going to be a 2D truss, and the other one is going to be a problem that involves beams and springs. Okay. So use that information as you will. So yesterday, hopefully everyone got my email. I posted the solutions for the problem set. I forgot that the problem set was due last night, so I guess technically you could have copied the solutions yesterday, but I was just telling someone before the class today that if you're just copying the solutions on the solutions just to turn it in, you are screwed for the exam. So you definitely want to make sure that you know how to do these problems. They're very lengthy. I know they take quite a while to do. And so, you're not really going to have that much time to think on the exam. And so you have to really know what you're doing, write down the matrices because you're going to be probably pretty much writing the entire time. Question? Oh, okay. Yeah, so just kind of make sure you're ready for that. Maybe bring like a hand warmer to rest your hand or something like that. Because it's even with only 2 problems. Typically, in my exam, I have 3 problem solving problems. Even with 2 problems, it can be lengthy, and so just kind of be prepared for that. I tried my best to kind of give you problems that don't involve just a ton of writing, but it's still, these matrices are really big. There's just a lot of numbers to write. You want to make sure that you use your time kind of effectively. Okay, and and remember, go for partial credit too. And so it happens a lot for this exam that a lot of people just don't have enough time to write down the entire matrices, especially for the boundary conditions. And so if you don't have time to write down the entire matrix, describe to me how you would do. So describe to me where you would assemble these matrices into the system. Describe to me how you would apply the boundary conditions, because then at least I can give you as much partial credit as I can. Okay. All right. Any questions on the exam or any questions on anything that we've covered so far?
Hey, Professor. Sorry.
Yeah.
So you said it's a 2-problem midterm, right?
Well, so there's two problem solving problems. So there's 2 direct fitness problems, but there's also going to be short answer conceptual questions as well. So there'll be four of those questions.
Gotcha. So overall 6, right? Or 4?
Yes. Yeah.
Right.
So the four problem solving the 4 short answer conceptual questions. In total, those will be 40% of the points.
Okay.
And the 2 direct stiffness problems together will be 60% of the points.
Okay. Got it. Thank you.
All right. Any other questions on the exam or anything I can answer before we get started? Yeah.
Would be able to use that one?
No. So there's no solving on the exam. So I'm only asking you to take it up to the point where you show me the final matrix. But you won't actually have to solve for this solution. Yeah, I know some calculators can do that nowadays, but even that would just take too long to punch in all the numbers. And so I mean, just writing down all the numbers already takes a long time, so. But I can tell, from the matrix, whether you know what you're doing or not, and that's what you get. All right, any other questions on the exam? Yeah. Second?
Do you accept bribes?
No. Maybe not now, but as I get more and more jaded with this job, maybe in the future, but not today. All right, any other questions on the exam? Okay, all right, so let's go and get started. Okay, so the lecture today has nothing to do with the exam, but it has something to do with your final project. And so, it's a little bit of a strange topic. It's not something that is it's not often covered in a lot of finite element courses, but it is really important. And in fact, I think if you look at any finite element study, whether it's in the primary literature or you work professionally, you have to do this to some degree. This is kind of an unescapable aspect of just modern finite elements. Okay, so the topic that we're going to go over today is called verification and validation. Okay. And so oftentimes you'll hear this be called V and V in the community. Okay. So, we're basically at the end of the semester at this point. And so, like I mentioned, there's not too much more for us to do. You guys know finite elements really well now, both from a practical perspective, but also, from a theory. Okay. And so at this point, we've been able to see that finite element simulations, or FEA, can be a very powerful tool for engineers. And it's a very powerful tool to help them with design and analysis. Basically, what it allows us to do in kind of its final form is to simulate or predict, what's going to happen in physical situations without actually having to try it out or without actually having to experiment. Okay? And that's really valuable, right? And so, when you're designing something, oftentimes when you're designing something, you go through certain, a certain amount of design iterations. You're changing dimensions, you're changing, materials, you're changing sizes, right? And each time you make an iteration, you want to find out how this part is going to perform in practice without having to actually build a physical prototype, right? And that is very valuable. But, despite all this power, despite all this usefulness, it's always important to remember that finite elements is just a tool, okay? And it's not a crystal ball either. So it's not that finite elements will accurately predict the future every single time. There are ways for finite elements to give you wrong results. Okay? And the reason for that is that FEA, it's not a future predictor, but we say that it is only a model of reality. Okay. And so you may, if you've taken me before, if you take me for a class before, you probably heard me use the term model. Because modeling is kind of a lot of what we do in engineering. Okay. And so a model is just kind of a way for us to describe something that allows us to make a prediction. Right? And so broadly speaking, a model is strictly a tool, but mostly, for engineering, we're basically looking at mathematical models. So models that are based on mathematical equations that are often, some kind of physical laws of the world. Okay. And this term is very broad. So let me give you an example to kind of illustrate this. Okay. So let's say that we were designing a cantilever beam and we're interested in the maximum amount of equivalent stress that is within the beam after we apply a load. Okay. Okay, so we have our cantilever beam. Let's say that we apply a force P at the end of it. Okay. And so what we want to do is we want to predict. Let's say we want to predict the maximum stress within this beam. Okay. So how can we do this? So, one way that we can do this is we can build a beam, a physical beam with the same dimensions and actually apply the load. And so, in other words, we can do a physical test, where that's often pretty inconvenient and kind of, not really practical to do. Okay. So if I were to give you this problem right now inside, and so I'll give you the dimensions of the beam, I'll give you the amount of force. Okay. I think most people in this class would probably open up ANSYS and CAD this up in ANSYS and give me, and then, apply the load and then give me the result. Okay. So that is one model for the problem. Okay. That's a pretty reasonable, I would say, pretty reliable way to do this. Okay. And in fact, everyone in this class is pretty well equipped to answer that question pretty well. Okay. But that's only one way to do this. And so that's only one model. Okay. Let's think of another model. And so another model, another way that we can try to form this prediction is we can ask my 10-year-old cousin to do the same. Okay. I just hung out with them, about 10 days ago. We went to an anime convention together. And the thing about 10-year-olds is that they're crazy. So I would buy him food, he would eat the food, he'd say, I don't like this. And so I would eat the food. And then he'd say, oh, never mind, I want it again. And so I'd have to eat it again after that. So, and he got me sick because he was coughing all over everything. But, I can ask him the same thing. So I can say, Turner, here is the beam, we're applying a force. What is the maximum stress in this beam? And, he would give you an answer. And he will say the answer is 12. Okay. And so you would ask me, what 12 what? What was 12 mean? Say 12. This is my favorite number. Stop bothering me. I'm gonna play Plants vs. Zombies. Okay. And so, even though this is kind of a ridiculous example, but this technically fits the definition of a model, right? And so it's a tool, it's a way for us to get a prediction of the stress within the beam without actually having to run a physical test, right? So even though this is kind of a crazy example, technically this is a model as well. Okay. But of course, not all models are made the same, and there's one model here that is definitely much more reliable than the other, and that's my cousin. No, it's ANSYS, right? And so if you were an engineer and you were designing this beam, you would definitely use ANSYS for this instead of asking your professor's 10-year-old cousin to predict this. Okay. Okay, so this first model here using ANSYS, this is the better model. Okay. But then that kind of starts to beg the question of, how do we know, which models are better than others, right? So this one here, it's kind of ridiculous. And so it's kind of obvious which one's better, but besides finite element analysis, there are lots of other computational tools out there that can also model the same thing. And even within finite elements, there are different ways that you can model a situation depending on how you formulate boundary conditions, how you do the mesh, okay? And so, you start to kind of see that, the definition of a model is very loose. And we need to be able to have metrics. We need to be able to have ways to compare and say which models are better than others. And believe it or not, there is kind of a systematic way of doing this. And that systematic way is to perform verification and validation. Okay. So that's the subject of today's lecture, and honestly, I think we'll probably carry over this a little bit into after Thanksgiving. But what we're going to talk about today is what do these terms really mean, and how do we quantify which models, or how do we quantify the goodness or the reliability of a model over another. Okay. Any questions on this so far? Okay, good. All right, so let's go ahead and define these. Okay, so these two things, even though they're often lumped together in the same sentence, they actually do mean different things. So let's go over verification first. Okay, so verification is the process of assessing the numerical accuracy of a simulation relative to the true solution of the underlying equation. I know that was a lot of words, but we'll go over what that means in a second. Okay. Remember, like I mentioned, that most models, at least most of the ones that are relevant to us in engineering, are mathematical models, right? And so there is some kind of mathematical equation, usually some kind of partial differential equation, that governs the behavior of our physical system. Okay? And the thing with partial differential equations is that they are very difficult to solve. And that's why we use FEA for them. And so, if you think back to the very beginning of the class, finite elements is nothing more than just a technique to solve these partial differential equations. Okay? But FEA, doesn't solve these equations exactly. Remember, FEA gives you an approximate solution to these equations. And so the idea with verification is to check and make sure that whatever you're getting out of your simulation actually is a good solution to that underlying equation. And so oftentimes, the way I think about verification is to ask the question of, am I solving these equations correctly? Okay. So this, of course, is a question of how you've implemented the finite element method, how it's programmed. Okay. Which for the most part, you as a user of a software like ANSYS are not going to have to worry about, because part of what you're paying for in using commercial software like ANSYS is that you're paying for the fact that they've already verified that their code works as intended. Okay. But there is still a little bit of verification that you have to do to make sure that your finite element simulation actually runs smoothly. Okay. And the main way that we're going to do this is through a mesh convergence test, which we'll review in a minute. But the other part of this is validation. So let's go ahead and define that term. Okay. So validation is another way for us to assess the accuracy and reliability of the simulation, but it kind of asks a slightly different question. Okay. So with validation, validation is the process of assessing the accuracy of a mathematical model relative to the physical phenomenon that's being modeled. Okay. So every finite element simulation is a representation of some kind of physical, physical phenomenon or physical situation. Okay. And so validation seeks to ask the question of, is our simulation, is our mathematical equations, is that actually an accurate representation of reality? Okay. And so kind of the question that you have to ask yourself with validation is not whether we're solving the equations correctly, but whether we're solving the right equations to begin with. Another way to kind of ask this question is, did we set up the problem correctly? So did we set up the boundary conditions well? Did we define the geometry well? Okay. So these are kind of separate things, right? And in order for a finite element simulation to be, valuable, right? You need to be able to both verify and validate your solutions, at the same time, right? Because on the one hand, you want to make sure that the situate or the equations that you're solving are, they actually represent your real situation. You want to make sure that your problem is set up correctly. You want to make sure the boundary conditions are accurate. And then once you have the problem set up, you want to make sure that you're actually solving it correctly, using the right software, making sure your mesh is okay. So, these are not new questions. And so these are questions that, we've kind of been at least implicitly asking ourselves throughout the class. But, with this lecture, I want to make it kind of explicit and just kind of, say that, these are kind of really important aspects of finite elements. But without these, you're kind of just doing art. Right, so you're just making kind of pretty pictures or pretty figures in the computer that don't really have, physical significance. All right, any questions on this so far? Okay. All right, so how do we do this, right? So these are kind of the definitions of verification and validation. In truth, as a user, right? So if you're using finite elements as just, you're just using ANSYS as a person within the company, honestly, there's not that much D&V for you to do. Right? Okay. And so for the most part, the bulk of verification and validation is done by whoever is developing the finite element software. So the people that are the engineers that are working at ANSYS, that are developing the software, right? It's mostly their responsibility to make sure that whatever code that they publish, especially code that they're selling to people, is properly verified, is properly validated so that it can actually be useful for people. Okay. And so if you look up kind of proper verification and validation, a lot of it has to do with, doing tests against benchmarks, doing validation experiments. We'll talk about that later. Most of those are done by the developers, and it's kind of the burden of the developers to make sure that their code is as reliable as possible. Okay. So unless you're going to be working for one of these companies and developing the software, the bulk of verification, or at least what kind of most people think of verification and validation, is not really your responsibility. So if that's the case, if it's not really on the user's responsibility to do V&V, then why are we even bringing it up to begin? Well, there is still some work that you have to do, right? Remember when we talked about our midterm project that, the main difficulty or the main thing that you have to communicate whenever you do any kind of computational work, whether it be finite elements or CFD or finite difference, is that it is up to you to convince people that the way that you run the simulation, the way that you set it up, is going to lead to a reliable result. Okay. Part of that is, properly justifying your decisions on the meshing, properly justifying your decisions on the boundary conditions. So that's kind of what we talked about in the midterm project. That's what you're gonna have to do for the final project, okay? But knowing kind of how V and V is done, will often give you kind of different perspectives or different ideas of how to do this, okay? So the whole reason, we're kind of going through this is to kind of give you more perspectives and more ways to show that your finite element simulation is reliable and that people can trust you and that your results are accurate, okay? All right. Because, as we kind of mentioned, many times in this class, there are, while FEA is a very powerful tool, there are a lot of ways that you can kind of mess it up and not really, give unreliable results. Okay. So I'm just gonna list a few here. So one way is to have, a poor mesh. Okay. Maybe you have a mesh that's not converged, or maybe you're not using the appropriate elements for a given situation. Okay. All right, so another way that your FEA results can be unreliable is that if you have incorrect boundary conditions. Right, so that's a big one, especially for your final projects. And so, I think this will probably be the most difficult thing for your final projects is coming up with boundary conditions that are going to be accurate for your situation. Okay. Okay. Of course, if you choose the wrong material for your simulation, that's also going to lead to incorrect results. Okay. And another way, that we're going to focus on, for today is, you have a situation that, I like to call you're kind of improperly modeling the situation. Okay. So improper modeling could be any combination of everything above it. It could be just something as simple as, you're choosing the wrong geometry, you're focusing on the wrong geometry. You're choosing the wrong equation. And so, maybe you have a static situation and you're trying to model it with the dynamics simulation. Maybe there's additional kind of thermal considerations that you have to account for that you aren't accounting for. So, there's a lot of ways with kind of improper modeling that you can kind of, mess up the situation. Okay. So what I want to focus on with verification and validations is kind of extra things that you can do, for your finite element study to increase the reliability, making sure that, you are making good decisions and, basically increasing people's trust in your simulations. Okay. Any questions on this so far? Okay. All right, so let's go through the first thing. So we've mentioned this, at least a couple times throughout the class, and that is mesh convergence tests. Okay. So mesh convergence tests, I would classify it under the category of verification. Because if there's one way to get your finite element simulation to not solve the equation properly, is to give it a poor quality mesh. Whether your mesh doesn't have enough elements, or maybe the elements themselves are poor or skewed or poor quality. Okay. Okay. So, we've talked about this before, that, the accuracy of your finite element simulation is kind of directly proportional to the size of the element in your mesh. Okay. And, after discussing this today, we can kind of know the reason why, that, the larger the elements, the more difficult it is to solve the underlying equations, correctly. Okay. So one thing that you have to do with almost all finite element simulations is you have to show that the number of elements in your mesh is enough to solve the equations possible. Okay. And so the way that you do that is through a mesh convergence test. And so, a mesh convergence test, basically, you're going to aim to run your simulation multiple times at different mesh sizes. Okay. So with mesh convergence test, you're going to run the exact same simulation. So you're going to keep the boundary conditions all the same. The only thing that you're going to change is the size of the element. And as you change the size of the elements, usually most people go from a coarse mesh to a fine mesh. And so as you refine the elements, the number of elements in your simulation is going to increase. Okay. And as the number of elements in your simulation increases, accuracy should increase as well. Okay. And so what you're going to do to do a mesh convergence test is that as you're changing the mesh density, plot out in a line graph the change in a certain quantity of interest. Okay. So with the mesh convergence test, you're going to be producing a line plot. And so, a lot of you kind of know this already because I saw that in your midterm project. But basically you would do something like this. And so you'd produce a plot like this, where the horizontal axis here, this is the number of elements in the mesh. And on the vertical axis, maybe some quantity of interest, maybe the stress in the system, or maybe the maximum deformation. Most commonly, people do a convergence test on the equivalent stress, but it really depends on the objective of your project. Okay. And then you're going to run the same simulation as the number of elements increase. And then as the number of elements increase, what you're going to see is that the result here should hopefully converge on a single value, right, or close to a single value. And in other words, the plot should, plateau. It may not be completely flat. You may still have a little bit of fluctuations. That's just kind of the nature of a computational, a computational simulation. But compared to, where it started with, it should kind of, stabilize around a certain value. Okay. And so what you can say is that, if you're running a simulation and you pick a mesh that's around right here, okay, so you pick a mesh density where, right about where the plot kind of stabilizes and kind of evens out, then you can say that your mesh is converged at this point. Okay. So this is really important, right? And so this is kind of the way that you show that your mesh is not only that you have enough elements in your mesh, but that your mesh is adequate enough to solve the equations as accurately as possible. Because the thing is, like I mentioned before, if your mesh is too coarse, it's not that, you're solving the wrong equations at that point, is that, the mesh is too coarse um, for the software to actually give you a good solution to that equation, okay? And that's why I kind of group mesh convergence tests under verification. That, remember, verification is all about, whether you're solving the underlying equation correctly. And if your mesh isn't adequate enough, or if your mesh is too coarse, then there's no way for you to solve those equations accurately. Okay. And so this is a part of every finite element study. And so you want to make sure that your simulation results are converged. Okay. Okay. Any questions on mesh convergence tests? Okay, good. All right, so that's pretty much the extent of what you have to do for verification, right? So remember, like I mentioned before, that for the most part, if you're using some kind of commercial software, the company that developed the software, or maybe the research group that developed the software, they've already done the verification for you. Okay. Oops. And so in case you're curious, so for a developer of FEA, right? So this is someone that works at ANSYS, or maybe someone that is developing their own open source research software. That's pretty common in the academic world. Okay. And so if you're a developer of FEA, when people say verification, what they usually mean is that they want you to run your code on some kind of test problem. or, another way that people call this, instead of test problems, that you're gonna run your code against, some benchmarks. And so the thing with benchmarks tests is that benchmarks are, problems that are run, many, many times. And so people already know kind of the true solution to these. And so to prove that your code, is solving the right or solving the equations correctly, you should get the correct answers to all of the test problems or all of the benchmark tests. Okay? So that's kind of the first thing that you have to do. But again, if you're just using ANSYS as a user, part of what you're paying for with ANSYS is that you're trusting them to have already run all the benchmark tests for you. And so you don't have to do it, but this is kind of just for your kind of information. Okay. Now, if you are going to use a different software, so we kind of live in the age right now where open source software are very trendy. And so, a lot of people are kind of downloading specialized code to run specific problems. These are usually developed by kind of small groups, or just a single developer. You want to be careful about using those kind of research open source softwares because, it's likely that they haven't run the software against, all of the benchmarks that are out there. Because these benchmarks actually take a while to do. These are not kind of trivial things. And so, I'm trying to think of some large projects. And so, one project that, my students have used is a CFD software called OpenFOAM. So I think, some of the people that are on the legacy team probably you've heard of OpenFOAM before. OpenFOAM is great. So, I don't have any issues with OpenFOAM. But, that's an example of a code that, people kind of Google something or they search for something and they download a code and they use it. And so you want to be careful kind of using these codes. Because a lot of things, if they're free, it usually kind of comes with some caveats. So, they may not be as reliable because, a lot of times, when you're in school and you're using, these reliable softwares like SolidWorks or ANSYS, you kind of get used to you kind of automatically start to trust, a lot of these softwares. But you kind of have to be careful, downloading some of these open source software because they're not all as reliable as SolidWorks or ANSYS. Again, OpenFOAM is great. I have no problem with OpenFOAM. OpenFOAM is run by a really great group. So, but I just use that as an example just because I know, that's an example of a code that people have done. Okay. All right. Any questions on verification? Okay. All right. So, the main thing with verification again is just the mesh convergence test. For the most part, you don't have to worry about verification on your own. Okay. So let's go to validation. Okay. And validation gets actually a little bit more complicated, just because it's a little bit harder to perform. Okay. And so if you remember from earlier today, validation is all about, whether your simulation is actually an accurate representation of reality. Okay. And so, in that sense, it's harder to do than verification because with verification, what you're asking yourself is that, we have this mathematical equation, is the solution that I'm getting, is that the correct answer to that equation? So that's much easier to verify because, you can solve that equation, especially if you do some kind of benchmark test, then, you can get the solution to the equation in a different way, okay? Validation is more difficult because, in order to check to see if your simulation is an accurate representation of reality, you kind of need to go out in reality and kind of touch graphs in order to get the data that you need. So validation, if you want to do kind of true validation, you need to compare your simulation results to some kind of real life, either measurement or real life data that you observe in the real world. Okay. So the most common way that this is done, for, at least for developers of FBA, is to do what's called a validation experiment. So a validation experiment, basically the idea with the study is to, create some kind of experimental setup in real life where you can basically, observe a physical phenomenon and do it in a way where you can take in as much data as you can, and then run a simulation of that exact same situation, and you try to get the exact same result between the two. Okay. So you're going to set up a physical experiment and simulation with exact same conditions. And you're going to try to get the same result. Validation experiments are really, I mean, they're needed, right? Because without validation experiments, you kind of just do whatever you want. But it's one of those branches of science that people often call kind of unsexy science. So, it's not really the most exciting work. But it's really important, and honestly, not enough people do it just because, part of the reason is that, academia is kind of really messed up and we don't value kind of unsexy work like this, but it's important because without validation, people can just write whatever codes that they want, and whether they are a representation of reality, we'll never know without the experiment. Okay, so let me give you an example of how one of these would be set up. Okay, so let's come back to our cantilever beam example. Okay. So let's say that, in reality, so this is in a lab somewhere. Okay. So in a lab, we create a prototype. So either we machine a cantilever beam, or maybe we 3D print one if it's not too big. Okay. We create a beam. Okay. Let's apply a force to the beam. Okay. And let's say that we set up this beam in a particular way where we set up, maybe we put a strain gauge on the edge of the beam. Maybe we take a ruler and we measure the exact deflection. Okay. So let's say that we put a strain gauge right here. Or maybe we use some kind of ruler or some kind of measurement and measure the deflection or measure the deformation here. Right. So basically, we set up an experiment and we set it up in a way where we can, get some data from the experiment. Okay. All right. At the same time, we set up the exact same situation within ANSYS. Okay. So in ANSYS, we create a CAD model of the beam, we load it into ANSYS, we mesh it in ANSYS, and we apply the load, we apply the constraints, and we run the simulation. Okay. So we have our fixed support, we have our beam. Okay. We're going to mesh the beam. And we're going to apply our load just like we did in real life. And then we're going to run the simulation, right? So by running the simulation, we're going to be able to compute the strain in the exact same location. Okay. We're going to compute the strain right here. And then we're going to compute the deformation and observe it at the exact same location as we did in the experiment. Okay. And so ideally, when you run these two tests and you get the data and you get the computation, both results are going to give you the exact same number. Okay. Oftentimes it's really difficult to get them to match exactly like right on the nose. But if you're within, 1%, 2% of the solutions in both cases, then what you could say is that your solution is valid. Okay. So that's kind of the gold standard for validation, right? And so if you're able to run an experiment and validate it, then this is kind of the best way to. All right, any questions on this? Okay, good. But you might be saying that the whole point of running a finite element simulation is to avoid doing an experiment to begin with. So doing a validation experiment kind of seems counterintuitive because if we're going to run the physical test anyway, we might as well just use the result from that. There's no need to bother using a simulation, right? And so the question that gets asked a lot is that do you have to validate every single situation that you are going to simulate within ANSYS? Okay. Because technically, whenever you change the boundary conditions, whenever you change the governing equation, that's technically a new problem. And so, if you really want to make sure that your results are reliable, you need to validate it against an experiment, right? But of course, doing so, like I mentioned, would kind of defeat the entire purpose of finite elements. And so typically you don't do this. Okay. So you don't have to validate every single situation or every single simulation that you want to do, but there should be some kind of validation on something similar to what you're simulating. And of course, I'm going to put similar in quotes there because similar is one of those kind of not exact words that we use kind of conversation with. So how similar is similar? Well, I would say that if you're using ANSYS and you're using one of the kind of established kind of equation systems like static structural, explicit dynamics, static thermal, you can kind of rest assured that ANSYS has kind of run the gamut of validation tests for those situations. And so if you're going to be using ANSYS and you're not going to be doing anything crazy exotic, usually you don't have to worry about validation too much. Because ANSYS, probably at some point in its long history has run some kind of validation, or maybe they base their code off another code that's validated. That's usually most common for people. Then there's no need to do that yourself. Okay. Now, with that said, a validation experiment like this kind of brings up an interesting point where if you are able to get data from a different source, and basically use that to prove that your simulation is accurate, that's always going to be valuable. So for those of you that are doing your final project on your senior design, right? I know for a lot of the senior design projects, especially the legacy teams, you've already done some tests, you've already done some experiments, and you already have some data. And so if you can use that data, if you already have something, you've already put it under, you put your parts under stress testing. If you can use that data to validate your simulation, that is fantastic. And so that would satisfy the validation requirement on the final project, is that, if you have data already available, or if there's a way for you to get data, that is, that's kind of the best way to do it. So, basically testing your simulation against kind of a real life situation and making sure that the data matches, that's kind of the best that you can do. Okay. Okay, but what if you don't have data, right? And so the majority of you guys doing your final project are going to fall into that situation. Okay? So how do you do validation without any kind of real life data or any kind of real life observation? Okay. So in most situations, you're not going to have data that's available to you unless you're explicitly, doing a validation study, right? And you can obtain data, but most situations you're not going to do that. Okay. And so in this situation, when you don't have experimental data to compare against, kind of the nature of the validation it kind of shifts a little bit. Okay. Instead of proving your simulation is correct, you can still do something to basically do some sanity checks to make sure that your simulation is not giving you outrageous results. Okay. And so even without experimental data, what I always tell people that you could always do some kind of sanity check, to make sure that your results are in the right ballpark. Okay. So this is where the validation calculation comes into play. So if you look at the specs of the final project again, part of the final project has you do what's called a validation calculation. So the idea with the validation calculation is to basically take your physical situation or take your simulation and compute some kind of result or some kind of, either deformation or stress using a method different than FEA. Okay. And so usually what I tell people is that, if you were to do this analysis or do this design without FEA, how would you do it? What equations would you solve? Okay. So think back, so I always tell people, think back to your previous courses, think back to your solid mechanics course. If you're doing some kind of structural problem, if you're doing kind of a thermal problem, think back to your heat transfer course. Even more basic than that, you may think back to your physics courses or statics or dynamics, right? How would you solve this, or what kind of calculation would you do, if you didn't have FEA available to you? Okay. So for example, right? So I keep coming back to the cantilever beam, but let's look at that again. Okay. And so, we have our beam that's like this. Okay. We have a single point load that's applied at the end. Okay. And just like before, let's say that we're interested in computing the maximum stress that's induced in this beam. Okay. So of course, one way that you can do this is that you can run a simulation in ANSYS in order to predict the results. But if you didn't have ANSYS, another way that you can do this is that you can solve the equation. Right? And so you think back to your 331 course, and you think back to to how you would solve it that way, right? And so let's say that you have a differential equations. We have E times A times D squared U dx squared plus some kind of body force B of x is equal to 0. Okay. Right. So you can solve this equation, solve this differential equation for the deformation U. Okay. So that, of course, would be something that you would solve by hand. You would apply your boundary conditions and all that as well, right? And so you would take your solution, your hand calculated solution U of x, and then compare that to your ANSYS simulation results. Okay. And then ideally, what you get from your hand calculation and what you get from your ANSYS simulation should match the same. Okay. They may not match exactly the same, just because this is obviously a highly simplified version of it, but you should be able to get somewhat close to each other. Okay. And so in that sense, you're basically using a hand calculation here to do a sanity check on your FEA simulation. All right, any questions on that? Okay, so one thing I will say though is that, for all of your final projects, they're gonna be a lot more complicated than just a simple cantilever beam, okay? Okay. And so it's gonna be too complicated for you to do a simple validation calculation on, okay? With that said, when you do a validation calculation, it doesn't have to be for your entire simulation. It can be for just kind of a small part of it or a subpart. Okay? So when you go to do your final projects, and you're thinking of your validation calculation, don't feel like that you have to do a validation for the entire structure, right? That's gonna be very hard to do for most of it. Right? So, be creative with it. So, maybe a critical component or maybe a small part that you can do kind of a simple calculation for, right? Now, I'll admit, coming up with a validation calculation and, coming up with a good, effective way to do a sanity check, it'll be a challenge for a lot of you. And so, if you're having trouble coming up with a good validation calculation, definitely come talk to me and we can kind of brainstorm together and we can kind of think of a way to validate your result. Okay? Because it's always, probably like you've learned in all of your other engineering courses, it's always worth it to do some kind of sanity check, do some kind of way to check your results. Because if you're just doing one method to solve this problem, that's kind of leaves you open to doing a lot of mistakes. Okay? And FEA is no different. Okay. All right, any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. And so next time I see you guys will be on Thursday for the exam. So remember, exam is only in person, so you have to come here in class. And so, I'm looking forward to seeing you all on Thursday. So, best of luck studying for everybody. Remember, I have office hours tomorrow from 5:30 to 6:30, and I have office hours on Thursday 1 to 2 for any kind of really last minute questions. But of course, you can always email me for any questions you have on the exam too. Okay. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see everyone here on Thursday.
Sure.
Sure. Yeah.
Yeah.
About the site question, like,
Yeah.
Right now.
like how you say your.
Yeah. So it depends on where the sources are relative to the so, the way we're doing the moments through is slightly different than the set. So now we're doing our pivot is around the center of the left. And so the way to determine these signs is when we're taking, that's what FMX is, for FMX, you kind of trace it around, it's going around this pivot here.
Which is true because
So that would be positive. That's why FK, that's why you're positive.
So.
Look at FKY, they have trace it around kind of the center node here, and it's going in the clockwise direction, so that would be negative. And of course, so people have asked me this question, so it really depends on how you draw the figure.
Not,
And so, in the homeworks, I think what I did was I kind of drew, instead of it going this way, I drew it this way.
Yeah.
And so that's gonna change the signs of those as well. And so, for these ones, it's really important that you draw your 3x diagram and make sure that your signs are consistent with that. Yeah, so the way you did this is good.
Yeah,
So the next one, usually, the way that you draw the next one, they're usually kind of in opposite directions, or opposite sides. of the center. So they're usually gonna have the same sign. And same for the Y, but the Y, something from the bottom here is going up, the Y from the top is going down.
No, well, the outside are more loaded.
Okay.
Inside, but then the rear would have-
I was confused. Thank you.
Yep. Hey, how's it going?
Right, because you're taking a fair.
Yes, yeah.
We're not taking a fair tire.
Yeah.
Right? It's like when you think of a ball, you're spinning on. Yeah.